Hey guys, so this week we looked at the work energy theorem. So like to go ahead and actually work through the quiz that we did. A lot of the questions can be answered just by looking at this quiz. Some of you guys are having trouble setting up the coordinate system, finding the force components, a little confused about when to just use the definition of work, when to apply the work energy theorem. So let's look at this problem. So go ahead and look at your copy of the quiz problem. It says, a block of mass m starts at the top of an inclined plane. The coefficient of friction between the plane and the block is mu. Assuming the block slides down the plane, calculate the work done by each force. So we have an inclined plane that looks like this. Okay, actually the other way around. We are given this angle theta, and we are given the height h. And that the block starts at the top at rest. And we want to find the work done by each force as the block slides from the top to the bottom. So we are looking at the path that the block follows from here to here when we calculate the work. Okay? What is the law or definition? Well, we're just calculating the work done by each force. So we go ahead and write that the work done from point R1 to R2 along the path followed by the force F is equal to the integral from R1 to R2 along that path of F, the force dotted with dr. And so we need to know what forces to apply this to. So we look at the free body diagram on the block. And we should have three forces. The easiest, of course, being gravity pointing straight down. And then the two forces, or the one force, from the surface of the ramp onto the surface of the block. That force has two components with famous names. The perpendicular component's called normal force, and the parallel component's called friction. It's opposing the motion, or rather, trying to slow down the relative motion of these two surfaces, and we know it's going to take on its full value, or its value mu n, whenever there's relative motion between the two surfaces. Okay, so we want to calculate the work done by normal force first. So, before we do that, we need to write the definition of normal force dotted with dr. And remember that this integral, let me fix this real quick. Remember that this integral here simplifies, and other than the one case where we have fx depending on y and fy depending on x, it will simplify to the integral of x1 to x2 of the x component of the force dx plus the integral from y1 to y2 of the y component of the net force, of just the force F in general. The net force needs to be used when we're applying the work energy theorem. However, we're just calculating work done. Okay, so for the normal force, we need to find its x and y components. So we absolutely, positively need coordinate systems to make any sense of this, or a coordinate system. And let's just use a coordinate system where, okay, it's probably easiest if I just copy and paste this picture and draw the coordinate system on it below. So let's go ahead and do that real quickly. Let's go ahead, so here's my picture. Let's go ahead and use this coordinate system where we have y straight out of the ramp and x straight down the ramp. Okay? And this is going to be my origin, 0, 0. So R1 is given by the coordinates 0, 0. And R2, my final position, which is down here, is given by the x-coordinate, which is going to be the length of this ramp, and the y-coordinate of 0. So let's figure out what the length of this ramp is going to be in terms of the given h and theta. Okay, so so we can say the length of the ramp is L, or the hypotenuse of the ramp is L. Then we have that sine of theta is h over L, so that L is equal to h over sine theta. Okay. So this is going from h over sine, from 0, 0. This block is starting at the top at 0, 0 to h over sine theta. Okay. So, the work done by normal force. Well, what's normal force's x component? That's this first fx here. It's 0, so nothing from the x direction. And what's the y component of normal force? It's n. So for the y integral, we have n. But notice that y1 is 0 and y2 is 0. So we have 0, 0. And there is no work done by the normal force. Okay, so that's the work done by my first force, n. Let's now go to friction. Alright, so before I move on, I want to go ahead and see if I can determine that n, using the fact that the sum of the forces in the y is equal to 0, to find n. Okay, and the sum of the y components of the forces is n minus mg cosine theta is equal to 0. And this tells me that the normal force is mg cosine theta. So just real briefly, how do I know that the y component of mg is mg cosine theta? We draw a coordinate system, xy, step 1. Step 2, draw the vector that you're breaking into components, mg. And next, drag over the angle from the picture to the coordinate system. Well, this angle theta is defined between a horizontal line and the positive x-axis. So it's going to be the same angle from a horizontal line I can put in there to the positive x-axis, theta. Which means if I draw a line which is parallel to the y-axis here, that this angle is 90 minus theta. And by the fact that this is a right triangle here, that makes this angle theta. Okay. So the x component is the component of this triangle, which I'll highlight in red. Okay. So there's the right angle and my hypotenuse. The x component is the component of the triangle which lies along the x-axis. That's this upper red line here. And since the hypotenuse is mg, we should have mg sine theta here. For the x component of, for the y component, yeah, mg sine theta would be the x component, but we're using the y component here since we're summing the forces in the y direction. And the y component, is this line down here, which is parallel to the y-axis, which is mg cosine theta, negative because this vector points in the negative y direction. Okay, or it points in the quadrant where the y values are negative. All right. So now that we know n is mg cosine theta, let's go ahead and calculate the work done by friction, where we know the friction force. Alright, so let's look at this definition. We integrate over the x direction, the x component of the friction force, and the y direction. Well, friction has no y component, so we'll just be integrating over x, so it's negative mu times mg cosine theta. And then we're going from our initial x coordinate, which is 0, right, 0, to our final x coordinate, which is h over sine theta, dx, and this integral is just a constant integrated over x, so we're just going to get negative mu mg cosine theta h over sine theta. And lastly, that's the work done by friction. So this is an F here. This is going to be called WF for the work done by friction. Lastly, there's mg, the work done by gravity. Okay, so we need the x and y components of gravity. But notice that once again in the y direction we're integrating from 0 to 0, so the y component of gravity will not matter. So we'll just integrate over x, So we're going from 0 to, once again, h over sine theta. And the x component of gravity is the first one I mentioned the last time that I was looking at this diagram. Okay, it is going to be mg sine theta, positive because we have a positive x component, dx. And this is equal to, well, it's a constant integrated over x, mg sine theta times h over sine theta. The sine thetas cancel, and we just get mgh for the work done by gravity. Okay, so we have our three answers. The work done by gravity is mgh. The work done by friction is equal to negative mu mg. Cosine over sine is cotangent, so I can write h cotangent theta. And the work done by normal force is 0. Alright, so I hope this was helpful. There's our answers. And you guys have a great weekend, and see you next week.